Good morning, students. Welcome to the session. Let us study the continuation of instruction set of MSP430 microcontroller. In the previous class, we have seen movement instructions of MSP430 microcontroller as well as binary arithmetic instructions with 2 operands. Today, let us study the remaining arithmetic instructions. With one operand. These instructions are also called as emulated instructions. The meaning of emulated instructions is it contains a single operand. The instruction contains an operand that is always a destination operand, right? Those instructions are called as emulated instructions. All these instructions, arithmetic instructions with single operand, are emulated instructions. Only we have a operand that is always a destination. These are emulated instructions which means the operand is always a destination operand. Right? Let us see what are those emulated instructions we have in MSP430. Serial number, instruction, description, example. First, under the instruction column, I will write the syntaxes. Syntax, clear, CLR dot W. You know this is data type, this is mnemonic. The data type can be a word or byte. If you want 16-bit access, you can write word. W stands for word, B stands for byte. Destination, right? This instruction is a emulated instruction because it has a single operand and that is always a destination operand. Clear.w BST. The description of this is clears the contents of destination, right? If you take the example clear.w R10, destination implies 0. As destination is R10, R10 implies 0. It is clearing the content of destination. When the content of destination is cleared, it should be 0. It is reset. Next, second one, syntax, DEC dot W. We also have decrement instruction in case of 8086 microprocessor. Here also we have a decrement instruction. So DEC stands for decrement. DEC dot W destination. The destination content is decremented by 1 time. By 1. Let us see the example. DEC dot W R5. So DST, that is destination, implies destination minus 1. Here destination is, this is destination, right? DST. So R5 implies R5 minus 1. So if you want to decrement the content of any register by 1 time, you can make use of this instruction, decrement dot W. Next, syntax. Decrement DE CD dot W DST. Double decrement. We call this as double decrement. We don't have this instruction in case of 8086 microprocessor. So the destination content is decremented by 2 here. If you take the example, DECD dot W R4, DST implies DST minus 2. Here DST is R4, R4 implies R4 minus 2. The content of this register is decremented by 2 times. Double decrement. This is single decrement. We don't call this as single decrement, we call only as decrement dot WDST. This is DECD stands for double decrement. Right? Let us see the next one. Fourth one, increment dot W DST. If you want to increase the content of register or destination by 1 time, you can make use of this increment register. Increment. The DST content is incremented by 1. You take the example, INC dot W R5. The meaning of this is destination implies destination plus 1. Here destination is R5. R5 implies R5 plus 1. So we have total 16 registers in MSP430. In all the 16 registers, R4 to R15 are general purpose registers. We can make use of any of the general purpose register as source as well as destination. Next one is double increment. Like double decrement, we have double increment. INC B dot W DST, double increment. Here the destination content is incremented by two, right? If you take the example incd dot w r6, the meaning of this is destination implies destination plus 2. Here destination is r6, r6 implies r6 plus 2, right? This is double increment. Next we have test. What do you mean by test instruction? est dot w destination. Here like compare instruction we have. What is the function of compare instruction? The compare instruction subtracts the source content from the destination content, and the result is not stored anywhere. Only flag bits are affected. In the same fashion, by using test instruction also, only flag bits are affected, but the operation related to test instruction is the destination is subtracted from 0, right? The destination is subtracted from 0 and result is not stored anywhere. Only flag bits are affected. So subtracts zero from destination and only flags are affected. Result is not stored. If destination is greater than 0, carry flag is 0, 0 flag is 0. If DST is less than 0, carry flag is 1, 0 flag is 0. If DST is equal to 0, right, the last case, 0 flag will be carry flag will be 1, because carry flag will be 0 because destination is 0 and we have 0. If you take the example PST dot W R7, here this is the destination. Destination implies destination minus 0. R7 implies R7 minus 0. Right? So test instruction operation is subtract. It has a single operand destination, that is it can be any register, general purpose register, and 0 is subtracted from destination. Only flag bits are affected. Result is not stored anywhere. So these are the emulated instructions we have, that is arithmetic instructions with single operand. Right? Let us see decimal arithmetic instructions. decimal arithmetic instructions. So we have two decimal arithmetic instructions, like we have decimal adjust accumulator in case of 8086 microprocessor. When you want to perform addition of two decimal numbers directly, so as we are dealing with hexadecimal numbers in this case, if there is a case of adding two decimal numbers, you can directly make use of this instruction, decimal add and decimal add with carry. There are two instructions, DADD, DADC. This is decimal add, decimal addition, decimal addition with add carry bit with destination. Let us see the first one. Syntax DADD, decimal add, source comma destination. So if you want to define the data type, you can also define the data type, whether it is a byte or word. DADD.W, source comma destination. What is the operand description of this? Source content is added with destination and result is in destination, right? So example for this is decimal add dot W R4 comma R5. The meaning of this instruction is this DST implies DST plus SRC. So here DST is R5, R5 implies R5 plus R4. The content of source is added with destination and result is placed in destination. You see here, this is source, destination. Source is added with destination, result is placed in destination. Next instruction we have decimal addition add carry bit with destination. Only we have a single operand here, and also this is a emulated instruction because we have a single operand, that is a destination operand. DADC, here add carry bit with destination. If you look at the example, .W R5, destination implies destination plus C. C stands for carry bit. Here destination is R5. R5 implies R5 plus C. Right? So it is also a emulated instruction. It has a single operand. Right? That operand is always a destination. Only two instructions we have under decimal arithmetic instructions, that is DADD, DA, DC. Let us see the next one. logical instructions with 2 operands and logical instructions with 1 operand. Logical instructions with the 2 operands. These instructions performs logical operations. These instructions performs logical operations like AND, XOR and bit related operations. And let us see what is the first instruction we have in this logical instructions with 2 operands. The first instruction is logical AND, syntax AND dot W, AND is the mnemonic, this is the data type, source comma destination, right? What is the meaning of this instruction? The content of source is ANDed with destination and result is placed in destination. ANDing is nothing but Boolean multiplication. So description, the source content is ANDed with destination and result is in destination. If you look at the example here, AND dot W R4 comma R5, register addressing mode. You can write any addressing mode. Indirect, you can also make use of indirect addressing mode, other addressing modes, whatever. Next, the meaning of this is destination implies destination and source, and is nothing but dot. Destination implies destination dot source. That is product. The content of source is multiplied with destination and result is placed in destination. Here the destination is R5. R5 implies R5 dot R4. The notation for Boolean multiplication is dot. Next, XOR. XOR dot W source comma destination. You know the XOR operation, right? When any one of the bit is high, the output will be high. When all the bits are same, the output will be low, right? It performs this logical XOR operation, also called as inequality. XOR gate is also called as inequality detector, right? The source content is XORed with destination and result is in destination. XOR, if you look at the example, XOR.W R4 comma R5, right? Destination implies destination XOR source. Destination implies destination. This is the symbol of XOR gate, right? Here R5 implies R5 XOR R4. If R4 is equal to, you can take the value and you can solve this. 0040H, R5 is equal to 0012H. How this can be written as? So I will continue here. R4 is equal to 0000 0100 0000. R5 is equal to 0000 0001 0010. XOR. For unequal inputs, the output will be high. For equal inputs, the output will be low. We have unequal inputs here. This is 0, 1, 0, 0, 1, 0, 1, 0. All these bits are zeros. This is 0, this is 0, this is 5, this is. So R5 contains 52. So here you will get 0052H in the result. The XOR operation of these contains R4 and R5 gives 0052. Right? The same fashion you can also take the example for this AND product. We product these two bits, you will get AND operation. Right? So next one. Third one we have bit the next one is bit. Bit dot W, this is the syntax, source comma destination. What is the function of this? So it performs bitwise test. Set flags only. So it performs a bitwise test and set flags only. If you take an example, bit dot W 0 hash, I will take immediate addressing mode here, hash 0040H comma R5. The meaning of this instruction is, you have given some data here, immediate data, and you are looking at this data with R5, right? This data corresponds to the bit position, whether this bit position in R5 is set or not. You are looking for the corresponding bit position in R5 is set or not. Is the meaning of this here I will write is bit 6 of R5 is set or not, right? So 0040H is nothing but 0040H is equal to 00000001000000. So R5 contains some data. So that in that data, this is 6th bit is testing, right? So is bit 6 of R5 is set or not? So this is the bit position. You have 6th bit position. In R5, this 6th bit position is set or not? It is testing, right? Like this, you can perform bitwise test. If you want to test 8th bit position in R5, so the data you have to assign is 0100H. 0100H. This will become 1 here. This will become the 8th bit, right? So like this, you can test any individual bit in any of the register. The meaning of this instruction is this R5 contains some data. In that data, whatever the position you have defined in the source bit position, by looking at that bit position in R5, whether it is set or not, it is testing, right? In this case, only flags will be set, right? Is bit 6 of R5 is set or not? This is the data. The meaning of this data is data contains 6th bit position. So you have to go for R5 again. You have to look for 6th bit position, whether it is set or not. Next instruction is BIS dot W source comma destination. This is bit select, right? So we have timers in case of MSP430. In order to initiate or start the timer, you can make use of this bit select instruction. Or else if you want to select the corresponding byte, whether lower byte or higher byte, you can make use of this instruction. Let us see the example. Example, bit select dot W hash 00 FFH comma R10, right? What it does, the meaning of this is set the lower byte of R10. So we have all ones in case of lower byte. So these ones are ended with the content available in R10. So we can select only lower byte in R10 with the use of this instruction. The lower byte of R10 is set. The higher byte is reset, right? As we have seen masking the bits in some programs of 8086 microprocessor. So bit select bit clear is nothing but masking, clearing and masking. Bit clear is nothing but clearing. This is bit select. So only lower byte is selected. With the use of this instruction, with this instruction, the meaning of this is the lower byte of R10 is selected. If you want examples, you can take. Next, bit clear dot W source comma destination. Syntax. This is also a syntax. DIC stands for bit clear. Here this instruction is used to start the timer. This instruction is used to stop the timer. Example, bit clear dot W hash. What happens here? In the previous case, we have set the lower byte (00) FFH, R10. Mask of the higher byte or clears the higher byte of R10. So as higher byte is 0, so the content in R10 is, higher byte content in R10 is cleared, right? This is bit clear. So there are 5 instructions under this category, logical instructions with 2 operands. They are logical AND, logical XOR, next bit test, bit set, bit clear. Also use, these 2 instructions are also used to start timer, also used to stop timer. A, we have timer A in MSP430. So in order to start and stop the timers, we can also make use of these 2 instructions. Let us see the instruction next one. Logical instructions with 1 operand. Logical instructions with 1 operand. So we have only one instruction, that is invert INV. It performs the ones complement. Let us see the syntax. Invert dot W destination. This is also an emulated instruction because it has a single operand, that is destination operand. So the description of this is performs ones complement of destination. If you look at the example, inv.w, if destination is R5, R5 implies R5 complement, right? We have only a single instruction under logical instructions with 1 operand, that is invert. INV stands for invert. Invert, you know, we have invert gate, NOT gate. It performs the ones complement of the given number. Here also it does the same thing. So this instruction contains a single operand, that is destination operand. So this is also a emulated instructions. Let us see next category, byte manipulation instructions. What is the meaning of this byte manipulation? You are manipulating the bytes, right? Whether the upper byte or lower byte. A word contains two bytes, lower byte and higher byte. If you want to manipulate the bytes, you can make use of these byte manipulation instructions. So there are two instructions named as SWPB, swap bytes. Next, SXT, extended sign of lower byte. If you look at the first one, swab instruction, what is the syntax you have here is SWPB .w src. It has a single operand, that is always source operand. So the meaning of this is description, it swaps the lower and higher bytes. Swapping is nothing but lower byte is changed to higher byte is changed to lower byte. Example, SWPB.w R5. If R5 is equal to 1032, this is lower byte, this is higher byte. After the execution of this instruction, R5 contains, after execution, R5 contains 3210. So here lower byte is swapped to higher byte is swapped to lower byte. See, this is higher here it becomes lower. This is lower now, this is higher. This is the meaning of a swap instruction. Only bytes are exchanged. Right? Within the word. Within a word. Is this clear? Let us look at the second one, SXT. SXT. This is extended sign of lower byte. The syntax for this is xxt.w source. So here the 7th bit of lower byte is a sign bit, so it copies the 7th bit in lower byte into 8 to 15 bits, right? Extended sign. Or else the other meaning is, if you want to convert a byte into a word, it converts white into word, right? Example is sxt.w R4. If R4 contains only 8-bit data, it can convert that 8-bit data into word, right? Next, we have only two instructions under byte manipulation instructions. So let us see the next category, shift and rotate instructions. The next category is not shift and rotate instructions, operation on bits in status registers. If you look at some textbooks, there will be no data type represented in these two instructions, byte manipulation instructions. In some textbooks, they can also write like this, xxt source. For this one, swpb source. Right? Don't get confused by looking at different textbooks. So what is the next category we have? The next category we have is operation on bits in status registers. Seventh one. We have seventh one under arithmetic instructions. Operation on bits in status register. We have a status register that is a 16-bit register. The size of the status register is 16-bit, right? So we have different flag bits in status register. They are negative flag, zero flag, signed overflow flag, and carry flag, right? So in order to set or clear all these bits, you can make use of these instructions. Operation on bits in status registers. So whatever the bits we have in status registers, you can control that bits, right? We also have a general interrupt enable bit, right? You can, if you want to set any interrupt, you can make use of this instruction. If you want to reset this interrupt, you can make use of these instructions. So there are 8 instructions under this category. First one is, so I will write the matter here, operation. Controls the bits in status. One is clear carry flag bit. So it clears the carry flag bit, clears or resets the carry flag. Next, clear negative flag, clears or resets the negative flag. Next, zero flag, clears or resets the zero flag bit. Next, STI, set carry flag SETC sets the carry flag bit. Next, set negative flag. Next, set 0 set 0 flag. Next, disable general interrupt. Disable general interrupt. We have general interrupt enable bit in status register. In order to disable this bit, you can make use of this instruction DINT. If you want to enable the general interrupt, EINT, enable general interrupt. So all these are the 8 instructions we have under the category of operation on bits in status register. So in order to control the bits, carry flag bits, and in order to enable and disable interrupts, so we have a control bits in status registers, so we can set or reset these bits in the status register by using all these instructions, right?